Hi, this is James Pickles, software developer at DNV. In this video, I'm going to talk about a Phast Excel add-in, which is a new way of running fast models directly from Microsoft Excel. First of all, I want to talk about the existing products that you are likely to be familiar with, which is Phast and Safety, and our CFD-based products, KFX and Exim. Our consequence and risk models have been developed over a period of more than 40 years, and we are continuously developing and validating them, which gives safety professionals confidence in using them. Our consequence and risk models are exposed through traditional desktop user interface, which caters for the needs of many of our customers. Now, what we see with our desktop tools, Phast in this example, we actually see many of our users taking data from Microsoft Excel and importing that data into the Phast desktop product, then running the calculations, and then exporting the results from Phast back to Microsoft Excel for further processing. So we asked ourselves, is it possible for the user to conduct all of their Phast work without leaving Microsoft Excel? And would this provide substantial efficiency gains? And that's what we've been exploring with the Phast Excel add-in. Now, in this demo, I'm going to talk about Microsoft Excel, but actually there are other ways of calling these models that are contained within the cloud. So, for example, you could use Python for running Phast models. You could create your own .NET-based application, or you could create a web-based application using, for example, TypeScript to run these Phast models. So here we are in the Phast Excel add-in. This add-in is installed via Microsoft's add-in store. And once it's installed, you get access to this Phast ribbon bar with a few buttons on there. What we also have on the right-hand side is a task pane, which contains information about how to get started and how you can obtain help in getting you up to speed with using the Phast Excel add-in. You can see in this particular workbook, I've set up a template, and I'm going to use this template to show you how you can run Phast models directly from Microsoft Excel. Now, this is just a template. You could use this template, or you could create your own template for solving whatever particular problems it is that you're trying to solve. Now, what we have up at the top is some tables for some input data. So here I'm going to specify the pressure in a vessel, as well as the temperature, the liquid fraction, and the material in the vessel. All of the data needs to be entered in SI units. So let's suppose we have a pressure of 100 bar, and then we have a temperature of, say, 300 Kelvin. I'm actually going to model this as a vapor release, so I'll specify a liquid fraction of 0 in the vessel. And then I'm also going to assume that the material is methane. And then from this vessel, we're going to model a leak. And we will assume that the hole size is 200 millimeters. And what I'm going to do in this demonstration is run a vessel leak discharge followed by a jet fire calculation with some radiation results. So therefore, we might be interested in different radiation levels of interest. So let's suppose we have criteria for immediate fatality, second-degree burns, and escape route impairment. Now for these, I will assume 37.5, 12.5 and 4 kilowatts per square metre. So we have our input data for running the calculations. So this might be data that you've already got defined within Microsoft Excel, or you might construct an entirely new workbook. So now that we've got our input data, we need to take that input data and create some Phast objects, which are building blocks for the calculations. Now, the first thing we need to do is determine the state in the vessel. For example, whether it's vapor or whether it's pressurized liquid. Now, for this, we can start to use some Phast functions that are made available via this Phast Excel add-in. We have entity functions, which are the building blocks for the calculations. So we need to use the fast.entity.state calculation. We give this a name. We can call it whatever we want. I will call it my state. And then we need to pass some entity property names into this calculation. So for that, we're going to pass the pressure, temperature, and liquid fraction property names, and then the corresponding values for those property names. And then we close the formula and hit return. And then we see the name return to the cell and also this symbol within the cell. We can click on the symbol and that opens up a simple user interface which tells us all about the data contained within that particular cell. So we can see the pressure, we can see the temperature, and we can see the liquid fraction that was specified in our table at the top. You can also see some other information. So you can see mixture modeling and also flash flag. So these are default values. If I wanted to override those values, then I could just simply amend my table up at the top to include flash flag, for example, and whichever flash flag I wanted to use. But because I was happy with the default flash flag and mixture modeling, then I didn't specify that information, and we can see in the card the default values that are provided. So we've created a state object. The next is that we want to create a material object. So we can see that the assumed material is methane. And then at this point, we can use a material function called fast.material.getMaterial by name. And then here we will pass the name of the material and then hit return. And what that actually does is that looks up methane in our database that's hosted in the cloud and returns the material object or the methane object. We can see it's got one of these symbols in the cell, so we can click on that symbol and we can reveal some information about methane. Now, because this is a single component, it's not too exciting at this point, but let's just assume for a moment we had something like LPG, which is a mixture. Now, when we click on that, we can see the components within the mixture. So we can see that LPG is assumed to be 70% propane and 30% N-butane. I'll change that back to methane. Now, what we want to do at this point is we have a vessel state and we have the material. What we actually want to do is run a calculation for telling us whether it's pure gas in the vessel, pressurized liquid, and so on. So for this, we can use one of the calculation functions. So fast.calc, and then the particular one we want to use is vessel state. We give it a name. I will call it my vessel state calculation. And then it's asking for a material and then a material state. So we can just reference those two particular cells, and then we can hit return. And then what that does is it sends the data that's contained in these two objects. It sends that data into our Phast models via an API. And then when the calculation is finished, we see the name of the calculation returned to the cell. And we have this calculator symbol, which we can click on. We can see the assumed inputs, so we can see the methane material and the state object. We can also see the output of the calculations. We can see that the calculation was successful, and what we're particularly interested in is this property here, vessel conditions. We can see that this is telling us that methane at the pressure and temperature that was specified is a pure gas. The next thing we want to do is we want to create a leak object. So we're going to specify some property names. All of these property names are documented. We have a documentation site which provides information about these so that you can get the syntax right. Now, we do have some functions for helping you understand this syntax. So we have a support function called fast.support.getEntityPropertyNames. And then if we just pass leak into that function, then that will return a list which tells us the names of the different properties within a leak entity or leak object. So we can see here the syntax for hole diameter and also the syntax for time varying option. So you can use those functions if you're ever unsure of the syntax of these entity property names. You can also look at these data cards to tell you the syntax. And we also, like I said, we also have a documentation site that shows all of this. So for this leak, we've got hole diameter and time varying option. So the hole diameter, remember this has to be in SI units. So we just need to convert that 200 millimeters into meters. And then we need to specify the time varying option. Now, again, we have a support function for this called getOptionNames. Now, if we pass time varying option into that function, that tells us the different options that are available for that particular option. So here we can say time varying rate. Again, that's documented on our documentation site. So next we want to create a leak entity. And this works similarly to the other entity functions. So we will say my leak. We give it the names of the entity properties, and then we give it the values for those properties. That's created a leak entity. And when we click the icon, we can see the hole diameter of 0.2 and the time varying rate as the time varying option. And again, we have some other information, which is default information that I was happy with for the purposes of this demonstration. Then, so we have a vessel state and we have a leak. We actually have to create a vessel entity. So for the vessel entity, the vessel needs to know the state, it needs to know the material, and it needs to know the vessel conditions. So for the state, we'll just take the state up here. The material, we'll just reference here. And the vessel conditions we actually get from the calculation. So if we point to the calculation and then press dot, so we've got equals C24 dot, then we can navigate down to the vessel conditions property, and that will return pure gas, which was the vessel conditions found in this calculation here. So we can pull out results from these cells very easily, just like this. Next, we need to create the vessel entity. So fast.entity.vessel, call it my vessel. And then as before, we pass the property names and the values for those property names. That has now created a vessel entity. You can see the material there, methane. You can see the state. We can drill down if we need to see the values. We can also see the vessel conditions there, pure gas. And again, there's other information in this vessel which has default values that I was happy with for the purposes of this demonstration. Now, what we need to set up now is what we call flammable output configs. So a flammable output config contains information about the harm criteria of interest. So for each of these radiation levels of interest, we need to create a flammable output config. So the first one is for immediate fatality. So that is the name that we will use for the flammable output config. Of course, you can give it any name. You don't have to call it immediate fatality, but that's what I'm choosing to do here. The entity property name in this example is radiation level. And then the value for the first one is 37.5. Hit return, and then we can copy that formula down 3 times to create a flammable output config for each of these radiation levels of interest. Now, one thing I forgot to do was the values need to be in SI units. So I need to multiply this radiation level by 1000 to get that into watts per square metre. We can take a quick look at one of these. So immediate fatality, you can see their radiation level is 37,500 watts per square metre, which is 37.5 kilowatts per square metre. Again, there's other information in this user interface where I was happy with the default information. Now, to run a vessel leak discharge calculation, a jet fire calculation and radiation calculations, there's some other objects that we need. The first is discharge parameters, and this is very similar to the desktop software. So you'll be familiar with many of these. Now, for the discharge parameters, I'm not going to provide any values, and that's because I'm happy with the default data in that particular entity. The next is we need a weather. I'm just going to call this day weather, but again, you could call it whatever you wanted. And I'm happy with the default data for the weather, so I'm just going to hit return. We can take a quick look at that. So this is the default data for a weather. Wind speed, 5 meters per second, stability class of D, and so on. Obviously, if you wanted to use other data, then you could set up a table just like the green tables at the top, containing wind speed, stability class, temperature, and so on. And you can pass that information into the function. Next, we need a flammable parameters. Again, I'm happy with the default. And then we need a substrate for the jet fire calculations. Again, I'm happy with the default information in that substrate, so I'm not going to change any of it. So now we've set up all of the objects that we need for running our calculations. Now for this, first we're going to run a vessel leak discharge, then a jet fire, and then a radiation. And we're going to pass results from one calculation into the next. So the first calculation is fast.calc.vessel leak. So we'll give it a name. And then this is asking for a vessel, a leak, and a discharge parameters. So we select those objects that were created earlier. We close brackets and then we hit return. And then this will take a couple of seconds. So whilst that calculation is pending, you'll see the cell just say busy. After the calculation is finished, then we see the name that we've given to this particular calculation. And then again, we see one of these cards. So then when we look at the data in the cell, we've got the input data, and then we've got the output data. We can see that the calculation was successful. And then we can see some discharge records. So if we click on this table, just to expand that a bit further, then this is a time varying leak. Therefore, each row in this table is a different time step during the release. So we can see from t equals 0 all the way down to just under t equals 11 seconds. For each of those time steps, we can see how the mass flow varies, or the release rate varies, the final velocity, the orifice velocity. We can see this storage state column has a number of storage state objects. So we can click on these symbols and we can see that for this particular time step, this was the pressure inside the vessel and the temperature inside the vessel. So all of the results from the calculations get stored in cells, and we have a very simple user interface for navigating the results to see exactly what it is that we might be interested in. And I'll show shortly how you can get those results out into somewhere else in your workbook for populating tables or producing graphs, whatever it is that you needed to do to complete your work. Now that we've run a vessel leak discharge, we're going to run a jet fire calculation. And we're going to pass the results from the discharge calculation, the vessel leak discharge calculation, into the jet fire calculation. So I'll call this my jet fire calculation. Now it wants to know a material. Now in this example, it needs to be the exit material from the leak, from the hole. So we can get that from the vessel leak discharge. So if we point to cell C43, that brings up a menu of results or data available within that calculation. We can select exit material. Then it wants to know the discharge records. Now, if you had your own discharge records, you could provide those discharge records in this jet fire calculation, but obviously we're going to get them from the discharge calculation that we ran over here. So again, we can point to cell C43, discharge records. Next, it wants to know how many discharge records are there. For this, we can use Excel's inbuilt count A function, and all of the fast count functions are compatible with Excel calculations. So you can have functions within functions, for example, like we've got here. So we're going to count the discharge records, just like that. Then he wants to know discharge result. Again, This is just information that's all contained within that vessel leak calculation. The reason it's asking for these different results independently is because it gives you the flexibility to provide your own if you wanted to do that. Then for the Jetfire, we need to provide a weather, a substrate, and a flammable parameters. Close brackets, hit return, and then after the calculation is finished, we see the name return to the cell, and then we can browse the user interface to look at some of the results from this calculation. We can see some messages that have come back from the calculation. So if there are any warnings, then or other messages, you'd see them appear here. You can pull those out into your workbook if needed. And then we can see some results. So on flame result, we can see the flame length, surface emissive power, and so on. We can also see some dimensions of the flame, or the geometry, the flame geometry. So we've done the Jetfire calculation, and then now we want to run a radiation calculation. So for that, we have distances and ellipses to radiation levels. Now, there's quite a lot of calculations available. As I mentioned before, all of this is fully documented. So you can get access to documentation that explains what each of these different calculations are. So here, I'm just going to call this my radiation calculation. Wants to know the flame result. Well, we've got that from the Jetfire calculation. Then he wants to know the flame records. So we get that from cell H43. Then he wants to know how many flame records are there. So we can count them just like that. And then the weather, the flammable parameters, the flammable output configs. Now you can actually pass multiple flammable output configs like that, so that within a single calculation we can determine the distances to each of these radiation levels, for example. And then it wants to know how many are there. Well, there's 3 of them. So we can close bracket, hit return, and then if we have a look at the results, we can see this distances result, which has 3 values. These are the distances to each of those radiation levels of interest. We can also see contour points, some X, Y, Z values, and we will use these for plotting some contours on a graph. So now that we've finished running the calculations, we will inevitably want to extract results from those and use those results in different ways. So there's a few different ways in which you can extract results, and you've seen some of that already. So let's suppose we wanted to get the initial or the maximum discharge rate from the vessel leak calculation. Then we can simply point to the cell. We can say C43.discharge records dot mass flow. That would actually return a list of mass flow values across the various time steps. So we're actually going to use Excel's max function so that we can actually get the maximum value. So that's one way in which you can extract results. The other way is you can actually navigate the viewer and pull results out. So let's suppose that we wanted that maximum mass flow value, which is here. You can highlight the value and then click this icon, and that extracts the results. And you can also, when you click on the cell, you can also click this icon and extract results just that way. This is returning a spill error because it's trying to return a list of discharge records. There's already data within the cells. So if we just move this over here, for example, then we can see all of the discharge record rows effectively in that table. And then if we click on this, we can say, I want the mass flow value, copy that down. That gives us all of the mass flow values. And then if we wanted, let's say, time as well, and copy that down, then what we've got there is mass flow versus time, and we could plot a chart with that data. So there's different ways in which you can get results out of cells. So here we want the flame length. So H43 dot flame result dot flame length. So it's very easy to get results however you want those results. So here we want the downwind distances to each of the different effects or each of the different radiation levels of interest. So we can get that from the radiation calculation. So M43 dot distances. That actually returns a list of distances, which are the downwind distances to those three different radiation levels of interest. So the next thing is, let's say we want to plot the radiation contours on a graph, then we can extract that data out of this radiation calculation. So we can see some XY values in this table. This is all of the XY points for the three different radiation levels of interest. Now, the formula is just ever so slightly more complex, but not too complex. So I'm actually going to copy the formula from another workbook, and then I'm just going to copy the formula into the table. So you see in the formula bar, I'm extracting contour points.x from cell M43, and then I'm just using another formula to, because all of the XY points for the three different radiation levels are bunched together in a single list, then we just need to extract the XY values for each radiation level independently. So that's why the formula is just ever so slightly more complicated. So we've got all of the XY points there, and in this template, I'd already set up a graph based on the data in these cells. So we can see here, for immediate fatality, second degree burns, escape route impairment, the different contours. Now, because the Phast calculations are run as part of a function, and that function is directly linked to the input data in our workbook, then once you've set up a template, it becomes extremely powerful and extremely easy to be able to change your input data and see the effect that that has on results. So if we note down here, the maximum discharge rate, 514 kilograms per second, and then I'm going to change the temperature in this vessel, that will automatically trigger the calculations to be run. When those calculations are finished, the results automatically update. You can even see that that chart updated itself as well. So let's just show that one more time. Let's say that instead of 100 bar, we want 50 bar. Hit return. You'll see these formulas have these green symbols. That means that the calculation is pending. And then after its update, you can see now we have some different numbers. The flame length is less than what it was because the pressure is reduced, and these radiation contours, the scale is smaller than what it was previously. So it's very easy just to change input data, see the impact on results, and perform lots of sensitivities. I want to show one other example of that. So in this workbook here, what we're actually modelling is a tank roof fire, which uses our standalone pool fire model and elevates that pool fire at the height of a tank. And we're actually interested in the thermal radiation at various points on a neighbouring tank. So this table here, each cell is a different point of interest on the neighbouring tank. Each column is effectively a different column on the face of the tank, and each row is a different height on that neighbouring tank. So this is effectively a grid of radiation values on the neighbouring tank. And obviously these are colour-coded based on the values in the cells. So here the values are in kilowatts per square metre. We've got our input data on the left. I've already set up this template so that the calculations are hooked up to this input data, which means that if I change some of this input data, so let's say we increase the diameter of the tank that's on fire, we would expect a bigger pool fire. So we would expect to see more red in this image. So I hit return. You can see the calculations are pending, and then now the calculations are finished. We can see significantly higher values of thermal radiation and significantly more red and orange on this particular chart. To show that again, let's suppose we change the height of the tank. So let's make it a 20 metre height tank. That's the tank on fire. So in this situation, we'd expect lower radiation values on the neighbouring tank because the neighbouring tank is further away from the source of the pool fire. So still quite a bit of red, but significantly less red than what was. So hopefully you can see there how powerful it becomes to just simply change your input data, see the impact on results, and perform lots of sensitivity analysis. Okay, thank you for listening. If you have any questions, please feel free to reach out at digital@dnv.com. Thank you.